A few months ago, Leia and I had a rather crazy idea to go diving under the ice in polar temperatures, but far from the sea ice, 5,000 kilometers from the North Pole.
The idea was to let ourselves slide into 2-degree water under a frozen high-altitude lake, protected from the cold by thick, dry suits. We hoped to find a magical filming setting under the ice, with clear and translucent water, so we could tell you about the vast sheets of frozen water that, in some places, cover our planet.
Unfortunately, this dive into a chilling unknown, this search for aesthetic images, turned out to be a flop, falling flat like a damp squib, subtitling. Because what wasn't supposed to happen, happened. Raw, unadorned nature made its presence felt. Torrents of water started pouring down in the middle of winter, even up to 2,100 meters above sea level. These exceptional weather conditions at this time of year left us dealing with zero visibility during the first few days.
Forced to search for a bit of light near the access holes, we moved forward by feel in this creamy, milky water, all shades of gray and white. Always holding on to our lifeline, our Ariadne's thread, so we wouldn't get lost in this thick liquid fog, thick enough to cut with a knife.
What a delicious irony it is to have come here to talk about the state of the white oceans and the frozen covers of the continents, only to be caught up by the reality of a part of the subject we wanted to address. Namely, the impact of warming on the ice expanses.
That explains the troubled origin of our footage. The hazards of filming in the wild will always be accelerated lessons in humility. And now that the ice of our disappointment has been broken, we can finally start tackling the heart of the matter. Namely, the ice cover, the white blankets that cover a little less than 7% of the surface of the oceans and 11% of the land on a global scale.
These icy expanses located at the poles, at high latitudes, and at high altitudes are essential for our planet. Without them, the Earth's thermal balance would be completely disrupted. The oceans would lose salinity, become more acidic, and warm up.
Because acting like a cold emergency blanket, the sea ice helps regulate the temperature of the open water and the oceans it covers. Like a mirror, it reflects the sun's rays, both in winter and in summer. Just think that between 50 and 85% of the light rays received by the sea ice are sent back up into the sky. This reflective power is called albedo, and it increases with the whiteness of the ice. For the dustiest glaciers or dirty snow, it's about 40%, but near our hole, with fresh snow, it can exceed 90%. On the other hand, with a reflective power ranging from 5 to 15% liquid water, doesn't compare at all. As this image shows us, you can clearly see the strong contrast in brightness between our opening in the ice, where the sun's rays penetrate deeply into the cold water, and the surrounding darkness.
And yet, we only have about 20 centimeters of ice above our heads. To add a few more meters, we would have to head towards the Arctic pack ice. That's where the members of the Under the Pole expedition, whose footage you're seeing now, went to carry out nearly 300 dives in order to study these frozen ecosystems up close. These are ecosystems whose ice covers, which constantly crack and break under the action of the wind and underlying ocean currents, can turn into real steamrollers, capable of crushing the hulls of many ships, and pile up to heights of 5 to 10 meters.
We now know that for these immense ice covers to form, floating on the surface of the Arctic and Antarctic oceans, when the polar winter sets in, the surface of the moving salty waters must drop below minus 1.8 degrees. Then, the first crystals, made up of a mixture of freshwater ice and tiny droplets of brine, can form.
At first, on the surface, the formation of ice creates a counterintuitive phenomenon. It will temporarily warm the surrounding air. Because by immobilizing the water molecules, which until then were liquid and subject to thermal motion, the formation of sea ice, the freezing, releases an amount of energy corresponding to that initial agitation.
Once the surface is frozen, the seawater is insulated from the cold air, and the formation process slows down, going from a few centimeters to just a few millimeters of ice per day. For several weeks, slowly, the sea ice thickens, gradually sinking into the first few meters of the icy ocean. And it's funny to think that if you put crushed young sea ice in a cocktail, you'd make a face, because it contains about 22 grams of salt per liter.
If the sea ice doesn't completely melt during the summer, then as it ages, it gradually loses its salt. Inside it, the salty droplets come together, gradually forming larger networks, then brine pockets, which, as if expelled, slowly return to the ocean. Therefore, sea ice gradually loses its salt. And as the polar proverb says, 1-year-old sea ice is good for nothing, 2-year-old ice is suitable for cooking, and 3-year-old ice is best for tea.
As long as it doesn't contain too many impurities, because when it forms, the sea ice traps and freezes everything that was in the water inside its huge ice blocks, suspended matter, phytoplankton, or air bubbles rich in CO2. And in doing so, it captures and traps a memory of the ocean at the moment it freezes.
Just like the gases from our regulators that make a vain attempt to rise and draw mercury-like puddles on our glass ceiling, ice, whether from lakes, the sea, or glaciers, contains a lot of impurities. Studying the ice above our heads is generally not very useful, because that ice has a lifespan that's too short to allow us, by studying it, to go back in time.
But those trapped for thousands of years in glaciers and polar ice caps are like samples frozen in time for us, containing within them the secrets of past climates at the moment when the bubbles were formed.
In reality, whether they're at high altitude or high latitudes, this massive ceiling of ice above our heads is much more threatened than threatening. In the Arctic, the ice cover has been fluctuating with the seasons for thousands of years, changing at the end of each winter with the arrival of summer temperatures. Its total area goes from 1.5 times that of Europe to half in just a few months. But it became clear that since the 1990s, the extent of sea ice that resists melting during the summer has been shrinking dramatically. And this decrease in the Arctic sea ice is accelerating. On average, it shrinks there by a total area equivalent to that of France. And while until then, the Antarctic sea ice seemed spared by the phenomenon, since 2014 its winter extent has also been declining every year.
And then, considering the sea ice only in terms of its extent is just looking at the tip of the iceberg, because the polar ice is also thinning, and this perhaps in even more worrying proportions. Because while the sea ice loses nearly 13% of its surface area per decade, it is estimated that its total volume decreases by nearly 30% over the same period.
Here is an animation that shows, in the Arctic, since the 1990s, the movement of the ice, the drifting of the frozen crust carried by the currents, buffeted by the winds. You can see the total surface area of the sea ice decreasing with the seasons, but also the thickness of the ice.
Over the past 30 years, the proportion of ice older than 5 years, shown here in light color, has melted away like snow in the sun, yet it is the oldest ice that is the thickest. And since their thickness partly determines their ability to persist, the phenomenon can only accelerate. It is estimated that each year, 318 gigatons of ice disappear. That's nearly a million semi-trucks.
If that image doesn't speak to you, just think of it as the soundtrack of the meltdown.
For almost 30 years now, the sea level has been rising by about 3.45 millimeters each year. And this pace is accelerating. Since 1993, the average sea level has risen by 9.3 centimeters. A little less than half of this rise is due to the expansion of the oceans and is a direct consequence of global warming.
In the Arctic, the air is warming, melting the sea ice, and the surface water of the oceans, now deprived of its shimmering protective cover, is warming in turn. Then, like a chain reaction, the surface waters, driven by their current, erode the surrounding sea ice, which, hollowed out from below, melts even more quickly.
On a microscopic scale, as temperatures rise, water molecules move more and more vigorously. And so, the sea level rises simply because the oceans start to take up more space. Just think, increasing the temperature of a 1 kilometer thick layer of seawater by 0.6 degrees makes it expand by 15.6 centimeters. Currently, this phenomenon of thermal expansion is responsible for nearly half of the rise in the average sea level.
The other half of this rise has nothing to do with the melting of the sea ice, which, since it already floats on the ocean, does not increase the ocean's volume when it melts, just like an ice cube sticking out of a glass doesn't make it overflow when it melts. The primary cause of this rise is to be found in the melting of part of the immense reserves of freshwater ice on our planet. Glaciers, polar ice caps, and the inland ice of Greenland. So much ice and eternal snow that are no longer truly eternal, now feeding the ocean with new cold water.
On, under, and inside the glaciers, the warmer meltwater flows riddle them like Swiss cheese before pouring into the polar oceans. Meanwhile, ocean currents can create gigantic underwater cavities that also accelerate the melting and calving of icebergs, ice caps, and glaciers.
For every degree of increase in the global average temperature, it is estimated that 800,000 square kilometers of glacier surface disappear, which is 1.5 times the area of France. And so, from trickles to torrents, from rivers to great rivers, the meltwater from the freshwater ice on the continents increases the level of the oceans, whose rise is not uniform across the entire planet. In some regions of the Western Pacific, the water level has already risen by nearly 20 centimeters over the past 30 years, while along the Canadian coasts, for example, it has remained almost constant. This apparent oddity is explained by the fact that, due to winds and currents, the increase in temperature and therefore the expansion of the oceans varies depending on the region of the globe. And then other strange geological phenomena also come into play to modulate and control this distribution.
Thus, it has been observed that the continental crust of Canada and Scandinavia has been rising since the glaciers that covered them disappeared at the end of the last glaciation, more than 20,000 years ago. But on our timescale, other adjustments are also taking place. When the glaciers of Greenland melt, the mass resting on the Earth in that area decreases, and the gravitational attraction there becomes very slightly weaker. To the point where, as a reaction, on the other side of the globe, in the South Atlantic, the waters begin to slightly accumulate along the Brazilian coast.
And then, the ice caps play a major role in the distribution and mechanics of ocean currents, which connect all the planet's oceans into a huge conveyor belt called the thermohaline circulation. Consider that when Atlantic saltwater reaches high latitudes are suddenly cooled here, their temperature dropping from 18 degrees Celsius to nearly 0 degrees Celsius. And this sudden cooling increases their density by about 3 kilograms per cubic meter. As a result, these now dense waters start to sink to more than 1,500 meters deep and head back in the other direction, dragging along this giant conveyor belt in their wake. At the same time, the sea ice, by freezing the water and releasing salt, also helps to make the surface waters heavier and causes them to sink.
All these reasons mean that the disappearance of this gigantic cover could eventually disrupt the global circulation, which is already affected by warming. And it's still strange to think that the presence or absence of a layer whose thickness, relative to the Arctic Ocean's 4,000 meters of depth, is far thinner than an eggshell is relative to an egg, can have so much influence on the global climate.
The Arctic and Antarctic are cold lungs. They are the frozen but beating hearts of the ocean system, and the consequences of their ongoing collapse are still largely unknown to us. We, hairless mammals, often have trouble grasping the scale of the problem. Industrial civilization, in some ways, is just like a Titanic that's too reluctant to change course, preferring to melt every iceberg in its path rather than slow down. Unable to face the fact that changes affecting places as inaccessible as they are inhospitable can be crucial for us and closely linked to the possibility of life in climate conditions favorable to us, we run the risk of taking on water from all sides.
And if the prospect of global climate change isn't enough to convince you to protect our icy survival blanket, maybe the argument simply lies in the desire to preserve the beauty of these milky, gray, luminous, white, pink, and blue environments. Clearly, projects as ambitious as these could not come to life without all those who, on TP, Utip, or through the join button, help us break the ice. So toss us a little coin in the hat and help calm us down.
A very warm thank you to the entire Under the Pole team for sharing their images and adventures with us. You can go and check out their giant icebergs on their channel, the link is here. Glug!